Hi everybody, today we're going to look at solving logarithmic equations, and this might be a little bit longer than my normal videos, so if you need to watch part of it and come back later, that works. But I want to provide a lot of examples so that you don't come across something that I didn't cover. So we're going to start by just saying there are two basic ways of solving logarithmic equations. One way is using the one-to-one property of logs, which means whenever log base b of x is equal to log base b of y, we know that x is equal to y. The other way is using the definition of logarithm, which is the log base b of y is x, means b to the x equals y. Generally, when you have logs on both sides of the equation, you're going to use the one-to-one property. When you have a number on one side of the equation, then you're going to use the definition of logarithm. And when I say when you have a number on one side, I mean just a number, not a number in a variable, or a number times a log, but just a constant on one side and everything else on the other. So, important note, as we're doing this, you want to make sure to check your answers to make sure it fits into the domain. So every once in a while you get something called an extraneous root that you're going to have to throw away. So I have this note probably at the top of every one of these slides to remind us to check our solutions, and as soon as it happens you'll be like, okay, I see what's going on. So let's start kind of nice and easy. I have the log base 3 of x equals 5. First thing I see is I only have one log and I have a number on the other side, which means I'm using the definition of log. So we're going to take the base 3, we're going to raise it to the 5th power, and we're going to say that's equal to x. I'm going to grab my calculator and put in 3 to the 5th, and it says that would be 243. The next one, I have the log base 6 of x plus 5 is equal to the log base 6 of 9. So we have a log on each side, which means I'm using the one-to-one property. In this video, we are not going to come across any times when I have different logs on the sides of the equation, so we're not going to have to worry about that here. Maybe that's for more advanced classes, but not for general college algebra. So the logs are the same. It means I get to drop them. I say x plus 5 is equal to 9, x is equal to 4. Checking the domain just says, is this number positive when I plug it in? So 5 plus 4 is 9. That's positive. We're good. We just go to the next one. Here's another one. I have log base 5 of 9x plus 3 equals log base 5 of 15. So logs on each side, that's a one-to-one property. 9x plus 3 is 15. Let's simplify that. Subtract 3. I have 9x equals 12. Divide by 9. Now I have x equals 12 and 9 are both divisible by 3, so let's make that 4 over 3. When you talk about answers, a lot of times we talk about exact and approximate. 4 over 3 is exact. If you put this in your calculator and you get 1.33 and it goes on, this is approximate. So I really wouldn't want to give that as the answer. I would want to leave it exactly as 4 over 3. Again, you can put 4 over 3 in, it stays positive, nothing really to do there except go to the next question. So the next one says log of x is negative 2. I have a constant on the right, a log on the left, that says we're going with the definition. What you should notice is there's not a base. So when the base isn't given, it's supposed to be understood to be 10. This is a common log. So this says I take the 10, I raise it to the negative 2 power, and this gives me x. Probably better to write 10 over negative 2 as 1 over 10 squared, which is 1 over 100. Now this time, if you want to put it in the calculator, or just know that this is equal to 0.01, it would be okay to give either of these answers because they are both exact. So decimals are okay and are exact if they have a finite decimal representation. It's when you have to start rounding because you see repeating decimals that you have to worry. So let's try some more. I have the log base 5 of 4x plus 5 is 2. I see a number on the right which says use the definition. So 5 squared is equal to 4x plus 5. I kind of write this kind of circle where I say 5 to the power 2 is equal to 4x plus 5. So I think going counterclockwise. This says 25 is 4x plus 5. 20 is 4x. X is 5. That plugs in, we're good. Next one, another common log. So log of x is negative 0.02. Let's rewrite it. Log base 10 of x is 0.02, negative. 10 to the negative 0.02 is equal to x. So if I wanted exact, this is exact, but let's also do an approximate. When I put it in my calculator, I get 0.954992586. I'm showing you everything I get. There will be directions saying how many decimal places to round to. Say that we're doing 4. Then we would look at 9549. This 9 would say round up. We would end up with 0.955. So here's another one. I have the log base 4 of x squared plus 7 is equal to 2. So first thing I see is I only have one log. I use the definition. 4 squared is equal to x squared plus 7. So 4 squared is 16. That's x squared plus 7. I move the 7 over, so now I have 9 is x squared. And remember, when you take the square root, to give both answers plus and minus 3, it's x. So I have two solutions. Luckily, when I plug them back in, the first thing I do is square them, which makes them positive. So they're both in the domain. So I do have two solutions this time. The next one says 11 is 8, natural log of x equals 36. First step would be move the 11 over. As we're going, we really want to isolate the x so that we can solve for it. So subtracting 11, I have 8 natural log of x is equal to 25. Then you want to divide by 8. So I have the natural log of x is equal to 25 over 8. So like the common log, the natural log doesn't write out what the base is, but it really is the base e. So we could rewrite it that way, which says e to the 25 over 8 is x. So e to the 25 over 8 is equal to x. This would be the exact answer. But sometimes we actually need to have some kind of scale of what the number is. So you could go to your calculator, put in e to the 25 divided by 8, and I'm going to give you approximate to 4 decimal places. So x is approximately 22.7599. So again, watch for the wording in the problem. It will tell you what you're supposed to do. Sometimes it will say both, which is good. It's nice to have the exact answer, but you also want to know what does that mean. So putting it in your calculator gives you a nice approximation. The next one says log base 8 of 5x minus 4 is the log base 8 of 4x plus 8. So 5x minus 4 is 4x plus 8. I move the 4x over, that's x. I move the 4 over, that's 12. If I put 12 in, I get positive, positive. Go to the next one. Log base 2 of 2x plus 5 is log base 2 of 13. 2x plus 5 is 13. 2x is 8. X is 4. So hopefully you're starting to see, I get what's going on. Looks pretty easy. I'm going to tell you ahead of time. It's going to get bigger as we go, so don't stop on the video yet. More is coming. This one says the natural log of 3x is 2.5. So let's rewrite that as the log base e of 3x is 2.5. So the first thing I want to do is rewrite this as an exponent. E to the 2.5 is 3x. And now I haven't solved for x yet, so now I have to divide by 3. So this is different. We haven't done this yet, where after we've rewritten it, that we do another step. If I'm looking for an exact answer, e to the 2.5 over 3 is the exact. For the approximate, I get 4.0608. All right, so I said it would get bigger, so here's where it really gets bigger. Is some problems require you to use the rules of logarithms before you solve. So remember, we have the product rule, the quotient rule, and the power rule. Looks like this. I have the log base 2 of x plus 1 plus the log base 2 of x plus 7 equals 5. I have two logs on the left and a constant on the right. So we have to rewrite this before we try to use one of our strategies. So here, because it's addition, we're going to use the product rule that says this is x plus 11 times x plus 7 when I put it together. So I have the log base 2 of x plus 11 times x plus 7 equals 5. Constant on the right says we're using the definition. So I'm going to keep the x plus 11, and I'm going to keep the x plus 7, and we're going to make the right side 2 to the power 5. So remember, you're going 2 to this power 5 when I rewrite it. So we're going to expand the left. I have x squared plus 7x plus 11x plus 77. 2 to the 5th is 32. So I have x squared plus 18x plus 77 is 32. Let's bring that 32 over. X squared plus 18x plus, when we bring the 32 over, I get 45 is 0. So I'm looking for factors of 45 that add up to 18, so that'll be x plus 15 and x plus 3. This says x equals negative 15. This says x equals negative 3. Now here's one where it's super important that I plug it back in, and what I'm looking for is when I add 11 and I add 7, do I have a positive? Well, negative 15 plus 11 is negative 4, so that says negative 15 is not in the domain. But negative 3 plus 11 is positive 8. Negative 3 plus 7 is positive 4. So that negative 3 is in the domain, and it is our solution. So see how we have to check for that extraneous root, which was negative 15, throw it away, and only keep the negative 3. The next one says 2 times the log base 7 of x is the log base 7 of 16. I have a log on each side, but I have this 2, right? This 2 in front that I need to deal with first. So what I'm going to do is move it up, use the power rule. So this says log base 7 of x squared equals the log base 7 of 16. Now that the logs are the same, I can cancel them. I get x squared equals 16. I take the square root. I get x is plus or minus 4. Think about plugging this back in, and you're plugging it into the original. So if I try to do 2 times the log base 7 of 4, I'm okay. If I try to do 2 log base 7 of negative 4, this does not work. So I want to say x is equal to 4 only. Let's try 3/4 times the log base 5 of x equals 2. This looks like the last one. We have this coefficient that we want to rewrite. So the log base 5 of x to the power 3 over 4 is equal to 2. So I moved this up. Now I can use the definition of logarithm that says 5 squared is equal to x to the 3/4. 5 squared is 25. So this becomes solving an equation with a rational exponent. And what we do is we do the reciprocal, which is 4 over 3. And we're going to do that on both sides. So my solution, this cancels out, and I just have x on the right. I have 25 to the 4/3 on the left. I don't know the cube root of 25. If I raise 25 to the 4th, yes, it'll give me a different number, but this really is exact solution here. If you want an approximate, you go in your calculator, you put in 25 to the 4 divided by 3. It says x is about 73.1004. Here's one that requires the quotient rule. I have the log of x plus 4 minus the log of x plus 3 as 1. So first step is to take this subtraction and turn it into division. So I have x plus 4 over x plus 3. This is equal to 1. Now this is common log, so remember this is base 10. So if I rewrite it, I would say 10 to the power 1 is x plus 4 over x plus 3. I'm going to multiply both sides by x plus 3. So this tells me 10x plus 30 equals x plus 4. Let's go ahead and move all the x's over. So if I take 10x minus x, that gives me 9x. If I take the 30 over to the right to the 4, 4 minus 30 is negative 26. I divide by 9, I divide by 9. So x is negative 26 over 9. What you want to do is plug that back in. So let's write that here. Negative 26 divided by 9 plus 4 is about 1.11. That's positive, that's good. If I do negative 26 over 9 plus 3, I get negative 1.89. This is negative, that's not good. Since that gave me a negative, it says I can't use this solution at all. It would have to fit it back into the x plus 4 and the x plus 3. Since it doesn't work in both, we're going to say this one has no solution. The next one says log base 3 of x to the 9th is negative 2. So I'm going to start 3 to the negative 2 is x to the 9th. If you want to rewrite that, you could. 3 to the negative 2 is 1 over 9. This is x to the 9th. I would take the 9th root of each side. Or if you want to write that as a power, you would write 1 over 9 equals x to the 9 and do the 1 over 9 power. Feels very circular there. So I have 1/9 to the 1/9. This is my value of x. It's positive, so I know that I can put it back in. If you want an approximation, x is about 0.7834. Let's try this one. I have the natural log of x plus the natural log of x plus 2 is the natural log of 120. They're all ln's, but on the left side, I first want to start with the product rule. I have natural log of x times x plus 2, natural log of 120. On the left, I have to distribute, so I have x squared plus 2x for my ln, and then keep ln of 120. Now I can drop the natural logs using the one-to-one property. So x squared plus 2x is 120. Let's set that equal to 0. X squared plus 2x minus 120 is 0. And then you look for factors of 120 that give you 0. Luckily, it's not too bad. That would be 10 and 12. I want the bigger one, 12, to be positive. Smaller one, 10, is negative. X is 10. X is negative 12. Think about plugging them back in. So 10 is fine. 10 plus 2 is 12. That's fine. So 10 works. But the negative 12 doesn't work even when I get to ln of x, so just one solution. But see how it's important? Plug it back in and check because you do have these extraneous roots. Let's do another one that uses the quotient rule. So I have the natural log of x plus 5 over x plus 4 equals the natural log of 3. This says x plus 5 over x plus 4 equals 3. Just like before, we are going to clear the fraction by multiplying by the denominator of x plus 4. So x plus 5 equals 3x plus 12. This x is going to come over. That gives me 2x. The 12 is going to come over. I get negative 7. So I have negative 7 over 2 is x. It might help to see that negative 7 over 2 is negative 3.5. I think that'll be useful this time because I think about negative 3.5 plus 5 is positive, negative 3.5 plus 4 is positive, so this is my answer. So that's our last one. I know that's a little bit long, but I hope it helped to see a lot of examples. Good luck as you keep studying logarithms. The next thing we'll really tackle is using this in the real world, so doing modeling problems, and I think you'll see that logs are very useful, and we just really have to have them to be able to solve exponential functions. Good luck.